I welcome you all to this round of lecture annotation video. This is the continuation of lecture number 4, processor basics. So let's move on forward. We will start at slide number 16. We have previously gone through these topics, and you have at least have the gist of this knowledge. I hope that you are understanding and practicing it well. So let's move forward. I had given you this slide as self-study. I hope that you do not have any problems. So let's begin with this slide. Other instruction design issues that we face while designing. How do we define the features or characteristics of a processor or microprocessor? Now the input or output address mapping, we see the input output map input output that which can be direct mapped input output. Therefore special input output instruction to access input output port. So if we require different instruction sets to access the input output port, it is kind of a problem, not a big one, but at least a smaller one comparatively. So then again, the memory mapped input output, the memory instruction accesses input output port. So when we require only to access the input output port or input output devices, and the processor redirects us to access the memory instructions or memory first and then input output, it creates a problem. So these are the issues. And the interrupt handling that we had to keep in mind to design a good processor, that is internal and external interrupts we need to take care of, and then the interrupts generated by the system or user software or hardware. And then again we need to check for these interrupts every instruction cycle. The instruction cycle is the ASM algorithm that we have seen earlier, algorithmic state machine. And from there we had seen that at first we have to fetch an instruction, increment the program counter by 1, and so on. So this is kind of totally a theoretical concept. So let's move on forward. So modern CPUs, how do they fare in the realm of speed and cost effectiveness? We get in here. So how do a modern CPU speed up? The answer is given right in this slide. They employ a variety of speed up techniques. Number one, cache memories. They use cache memory so that the fetching is kind of faster to the CPUs, and they use special purpose instructions, test and set. For example, if we test memory and we find the required data there, we set the data in the accumulator, etc. The MMX special type of instruction. And then the redundant hardware modules, superscalar and very large scale integration, etc. is present in the modern CPUs. And the another one is very important, parallel processing. It is kind of similar with the notion of threading. We have seen at least this keyword kind of in Java when we were learning the object-oriented programming course. And Another concept which is used to speed up the CPUs is pipelining. I have told you before that we will face this term literally many times and during this course, and during the issues we will face in the future. So simple two-stage instruction pipeline, we will get to the figure there. Two-stage pipeline is consisted of fetch and execute. We will see in a little bit. Now, what happens if a branch occurs? The pipeline must be flushed. So, what happens if a branch occurs? And that is, we encounter some subroutine or some branches or some go tos or up level, go to a specific portion in the program, etc. The pipeline is completely destroyed, flushed, and it needs to be written or set up again. So that is what is going on in here. And then we have this very familiar or the standard microprocessors, ARM6. It is the modern 32-bit RISC microprocessor. We will go in a bit to the RISC and CISC microprocessor and the difference between them. So bear with me for a bit. And the ARM6 microprocessor is the standard or very common microprocessor of the RISC type. Has a file of 32 bits general purpose registers. In user mode, 16 32-bit registers R0 to R15. That is, we have R0 to R15, that is 16 register, which have a size each of 32 bits. That is, R0 is 32 bit, R15 is 32 bit, which is visible. Has a load store architecture. Only load and store instructions can access the memory, and all others use these registers, and uses an instruction pipeline. So we store in a pipeline the instructions that were to be executed one after another, and these instructions are stored in a pipeline. And then we have Motorola 68020, which is a slightly old 32-bit CISC microprocessor. It has registered file of 32 bits registers, 8 data and 8 address, a large number of instructions and addressing modes, and it uses memory mapped input output, does not use a load store architecture. That is, any data or address can access the memories. So it does not use the load store architecture. So you have to remember it a lot. And now, as I have told you before, we have come to the point where we understand what is RISC and what is CISC. RISC is the full form of RISC is reduced instruction set computer. Therefore, the abbreviated alphabets are included, are marked in the slide. Reduced, we get R from this word. Instructions I, sets S, and C from computer. And the CISC architecture has complex instruction set computer. There are many ways basic design of CPU can be improved. Therefore, most recent CPUs contain the following extensions which improve the performance and case of programming. Multipurpose register for storing data and address. That is, a register can hold both data and the address in them. So therefore it's multi-purpose. If it only stored only data, then it would be a single purpose register, or if it uh, had stored only address, it would have been called single purpose register. And the additional data instruction and address type is always available, which further speeds up the performance. And the register to indicate computation status is present, and the program control stack. So it's a very important task of every computer to get the instructions fetched up and to get the instructions as quickly as possible. So it's very important here. So now let's move on forward the topic of pipeline. But before that, show you I would like to show you another topic, the difference between RISC and CISC. It is given in your resource Google Drive. So this is totally your self-study. You study it, and if you have further problems, please consult me. So it's already given in here. Let me mark it again. This is the CISC and RISC difference. So study it well. So let's go back to the topic of pipeline. So pipeline, we have already learned about the pipelines when we hear about gas pipelines, we hear about oil pipelines and so on. So what is this pipeline in computer science? Our computer science always fetches the real-time terminologies from our real life. So this pipeline is the pipeline of instructions. So this pipeline is the pipeline of instructions. Now, modern CPUs have a variety of speed-up techniques, including cache memories and several forms of instructions that level or that kind of likes to have a parallelism. Such parallelism may be present in the internal organization of DPU, data processing unit, or in the overlapping of the operations carried out by the DPU and the PCU, program control unit. These features add to the CPU's complexity. So if we are to incorporate this pipelining feature, we have to increase the CPU's complexity. That is a must. So let's move on forward. So here we get a glimpse about the description. Uh, I'm going to read out and try to explain on the go. Overlapping of instruction fetching and execution is an example of instruction pipelining, which is an important speed up feature of RISC processor. So we are concerned here about the RISC processor, and as I have told you before, this is the instruction pipelining, and it fetches the instruction and executes it. So these are the stages of pipelining. Each instruction can be thought as a passing through two consecutive stages of processing: a fetch stage, implemented mainly by the PCU, and execution stage, implemented mainly by the DPU. Hence, two instructions can be processed simultaneously in every CPU clock cycle, with one completing its fetch phase and the other completing its execute phase. This simultaneous process is called two-stage instruction pipeline. So if we have two stages of the instruction pipeline, then it is called the two-stage instruction pipeline. We will see more stages of instruction pipeline later on. So let's discuss this first. The first one is the I1 instruction, and this is the second instruction I2, and this is the third instruction I3. This is the first clock cycle, this is the second clock cycle, and this is the third clock cycle, and this is the fourth clock cycle. As we are observing in here that we have the fetch stage of the instruction I1, and when we are executing the instruction I2, the CPU sends I2 to be fetched. So this is a kind of two stage of the pipeline, that it has performed this fetch task earlier for the previous instruction, and while that instruction is being executed, we fetch or we try to search for the next instruction, and when we execute the next instruction, we get to fetch the next instruction, that is the I3 instruction, and so on. So this is the overlapping instruction in two-stage instruction pipeline. So these are the main concepts. So once again, we are burdened with the fixed point and floating point of representing numbers or values that we encounter while accessing the memories or calculations in the machines. So fixed point formats allows a limited range of values and have relatively simple hardware requirements. So if you are asked about what is the simplest form to represent numbers, it is the fixed point. Why? Because it represents a limited range of values and have a relatively simple hardware requirements. On the other hand, if we encounter the floating point numbers, it allows a much larger values but require very costly processing hardware or a lengthy software implementations. So what essentially goes down here is that floating point needs a very large amount of processing capabilities, either hardware or software. Now let's move on to the next slide. So what we have here is the fixed point number and some description of it. So the number types to be represented, for example, integers or real numbers. To represent the numbers, the scope is actually great in fixed point numbers, greater than the fixed point numbers. We have a limited amount of numbers to be represented, and the range of values is kind of limited, and the precision of numbers, which refers to the maximum accuracy of the representation, is kind of limited, because we don't know how much the memory can take of this fixed point number. And then the cost of the hardware required to store and process the numbers is always present in the fixed point numbers. So this is all about this lecture. I hope you get this lecture in full format as it is. If you have any problems understanding this, please ask me in the Google Meet, and I would give you this task also, going through with this CScan risk PDF. Please read it And if you have any questions regarding this topic also, consult with me when we resume in Google Meet. Thank you for listening to my lecture. I hope you get this topic. See you in next video. Thank you.